Imagine an object so powerful it could challenge the most fearsome monster in the universe, the black hole. For decades, black holes have been the ultimate cosmic dead end. Nothing escapes, not even light. But what if there's something else? Something that looks like a black hole, acts like a black hole but is fundamentally different inside? Enter the Gravastar, a gravitational vacuum star. This idea could solve some of the deepest paradoxes black holes present. Think of it as a cosmic plot twist, a new fate for dying stars. When a massive star collapses, does it have to become a singularity? Or could nature have a clever alternative? The Gravastar suggests nature avoids infinities, offering a mind-bending way out of the black hole conundrum. So, let's journey to the heart of a dying star and witness the birth of this cosmic enigma. We'll peel back its layers, compare it to black holes, and explore how we might prove Gravastars exist. Somewhere out there, Gravastars might be hiding in plain sight, challenging everything we know about gravity and time. To understand Gravastars, we first need to witness the death of a giant star. Massive stars live fast, die young, and end in spectacular supernova explosions. For millions of years, nuclear fusion in their cores fights gravity's relentless pull. But when the fuel runs out, gravity wins, catastrophically. The core collapses in a fraction of a second, triggering a supernova that can outshine an entire galaxy. What's left depends on the core's mass. If it's not too massive, quantum pressure halts the collapse, forming a neutron star, a city-sized sphere of unimaginable density. But if the core is even heavier, not even neutron pressure can stop it. The collapse continues, crushing the core to a singularity, an infinitely dense point. This singularity is surrounded by an event horizon, a one-way door from which nothing escapes. That's a black hole, the traditional endpoint for the universe's most massive stars. But is that the only possible ending? Some physicists think there could be another way. The Gravastar offers a radical alternative to this cosmic finale. Let's see how. For decades, the story ended with neutron stars or black holes, but the idea of a singularity, a point of infinite density, signals our theories are breaking down. Nature doesn't like infinities. Could there be a third option? Enter the Gravastar, proposed by physicists Mazur and Mottola. What if a collapsing star is halted just before an event horizon forms, thanks to a phase transition in spacetime? Instead of a singularity, the Gravastar has a bubble of pure energy, dark energy, at its core. This dark energy pushes outward, balancing gravity's inward pull. The bubble is surrounded by a thin, ultra-dense shell of exotic matter, a quantum state we can barely imagine. This shell forms the surface of the Gravastar, separating two radically different phases of spacetime. On the outside, it looks like a black hole. On the inside, it's something entirely new. The Gravastar is a cosmic imposter, almost indistinguishable from a black hole but fundamentally different. Picture a Gravastar as a cosmic egg, a hard, thin shell with a bizarre interior. The shell, only a few Planck lengths thick, is made of exotic matter, unimaginably dense and strong. Inside, there's no matter, no singularity, just a quantum vacuum filled with dark energy. This dark energy pushes outward, perfectly balancing gravity's inward pull. The result? A stable equilibrium, no collapse, no infinite density. The Gravastar sidesteps the singularity problem, keeping the laws of physics intact even in extreme gravity. It's a bridge between general relativity and quantum mechanics. The shell is a quantum object. The interior is ruled by relativity. To truly understand Gravastars, we'll need a theory of quantum gravity, a frontier we haven't reached yet. Gravastars point the way toward a deeper understanding of reality. They offer an elegant solution to the messiest problems in black hole theory. Instead of a breakdown, we get a new kind of cosmic order. The Gravastar is a signpost to the next revolution in physics. If Gravastars exist, how could we tell them apart from black holes? From a distance, they're nearly identical, dark, spherical, warping spacetime, devouring anything that comes too close. Both are cosmic traps, but the key difference is at the boundary. A black hole has an event horizon, a point of no return, not a physical surface. Fall in and you're gone forever. Information is lost at the singularity. A Gravastar, though, has a real, ultra-dense shell, a physical surface. It's not a soft landing, but it's a place, not a mathematical boundary. This means information might not be lost, it could be preserved in the shell. The Gravastar acts more like a cosmic storage unit than a shredder. This subtle difference, a hard surface versus a one-way door, could solve the information paradox. It's what separates Gravastars from black holes and might one day let us tell them apart. The universe could be hiding these imposters in plain sight. The challenge is finding a way to reveal them. If gravastars are such convincing black hole imposters, how could we ever find one? The answer may come from gravitational waves, not light. In 2015, LIGO detected gravitational waves, ripples in spacetime from colliding black holes. When two black holes merge, the new black hole rings like a bell, emitting a smooth pattern of waves. But if two gravastars merged, the aftermath could be different. The hard surface of a gravastar could trap gravitational waves, causing echoes like shouting in a cave. After the main burst, we might detect faint, delayed echoes, signatures of a physical shell. Detecting these echoes is tough. They're faint and buried in noise. But as our detectors improve, we might hear them. Finding these echoes would be monumental, evidence for physics beyond Einstein. It would prove these exotic objects are real and force us to rethink gravity and the fate of stars. The universe is speaking in gravitational waves, we just need to listen for the echoes.